My name is Sebastian Winkler. I'm hosting this from Berlin in Germany, and I welcome all of you to our webinar, How to Get Precision Mineralogical Data on Your Full Drill Campaign Quickly. And if you could use the chat to tell us from where you join us, that would be lovely. I'm joined here on stage by Bernd Hinrichsen, who holds a PhD in mineralogy, uh, was working at the leading manufacturer for lab XRDs, Bruker, for a while, and then managed the world leading structure solutions lab at BASF before he actually had the idea to our very great service and is now our chief science officer here. And I'm joined by Callum Clark, our expert for mining customers and a geologist with extensive field experience. And we are going to cover um, today in our very short session when do you need mineralogy? What can you use today for getting mineralogical data? We're going to dive then a little deeper into XRD. What is an XRD actually measuring and how does it work? We're going to then work towards the synchrotron XRD and what actually improves and where it doesn't. And then very shortly, I'm going to tell you a little bit about data logistics and costs and how to get this. So with that and no further ado, and then we're going to have a long and extensive Q&A, and you can ask us any questions you like, preferably about mineralogy. But with that and no further ado, I'm going to give it over to Callum.
Cheers, Sebastian. So yeah, as he mentioned, I've worked as an exploration geo for the past over 5 years in Europe and in Australia. So I've seen a lot of use cases in mineralogy, a lot of what people do and don't do. Obviously, there's a need for mineralogy across the board in geology and in mineral deposits. Also, we have a graph here that shows a kind of when it's utilized and when it's essential. From one extreme, we have coal, which I haven't personally worked in, but I believe it's quite straightforward. When you're in a coal seam, you can see the organics and the chemistry kind of backs that up. And then you would use mineralogy maybe as pathfinders or to tell you the alteration zones. And then as we come further across on this graph, you can see that the mineralogy might get a bit more complex, or the ore deposits are more complex. And then when we get to copper, nickels, we're looking at, sulfides versus oxides, what sulfides we have, what phases we have. It makes a difference if we're going into a mine and for flotation. And then also in lithiums, where we want to understand exactly what phase is hosting the lithium. And also we might be surrounded by more clays, and in clay-rich areas, it's very important to tell kind of clays how they act under certain conditions for when we finally go through onto our metallurgy test work. So we have a little poll here that's kind of asking you guys how you currently get your mineralogy data. Your core logging, auto logging, calculated from chemistry, or ChemScan, or LabXRD. I don't know if you guys want to put in your answers into the poll quickly, but normally I would guess that most geologists, most people out there will just be kind of looking at the core and then maybe sending off for classic assays and just getting back the calculated chemistry. So I'll talk a little bit about which each technique is. Obviously, core logging is the basic tool that everyone uses. There'll be a geologist on the drill rig and he'll be listing what he sees. There's also auto loggers now, which I think everyone might be familiar with, where you send off to a lab and they can get you a basic mineralogy scanning your drill cores. Obviously, there's a fair amount of cons with this technique. Every geologist is very subjective. What to me might look like 5% of a mineral might be, 20% to someone else. Well, maybe not 20%, but within reason, there's quite a lot of variability. Um, Obviously, human eye isn't the best at actually determining what mineralogy we have. And the same can be said for actually the autologgers, where they're very good at picking up changes, but they might not be the best at individually picking out your mineralogy. And then from that, we normally lead into the assays, and people use assays and core logging to kind of calculate their mineralogy. It's very good for getting a mineralogical number for each drill meter. Obviously, this isn't quantitative, and it's more of an estimate and taken as a model to guide your drilling rather than telling you what is actually there. Pardon me. And then we have, well, ChemScan, which at the moment I believe is one of the gold standards for kind of getting your mineralogy, with texture, liberations, to understand how your minerals are sitting in your rock. It's very useful for before you go into any testing and metallurgy. You also get these lovely, nice pictures of your rock, and some of them will also tell you the chemistry of the grains. Obviously, this is pretty expensive. You can take a long time to actually get your results back. It's not super good at doing your whole drill campaign. Well, not at all. You need to be selective in what you're sending in, and it's limited by grain size. So if you are working with anything below, I think 100 microns, then you just won't see it in the chem scan, and you might be missing out on a large bit of your mineralogy. So that's kind of covers everything that we use currently, and I'll leave the expert to talk about the classic XRD. And
thank you very much, Callum. Yes, now I'm very excited to tell you about laboratory X-ray diffraction. This is something that I've been doing my whole career, as long as I was at Bruker, obviously, and then also at BASF, and it is a wonderful technique. Otherwise, I wouldn't have been doing it for so long. You have your sample, you prepare it into a flat plate typically, and then move your X-ray tube and your detector at the same velocity along an angular range, and measure the diffraction signal. It is really great if you have it in your lab and you can access it quickly. It's a wonderful technique. It is perhaps a little challenging when it comes to a certain aspect. So detection limits are one of the most difficult ones. Yeah. So you do have very solid detection limits, depending, of course, on your mineralogy very strongly. That can sort of be in the order of about 4 or 8%. Yeah. So your trace phases will definitely not show up in your laboratory devices. Yeah. If you want to do a lot of samples, it does get rather tedious, as these machines do require a decent amount of time to collect good data. Plus, if you have a copper tube, which in my experience, 99% of the instruments out there do have, you do have serious issues with fluorescence for all the elements that come below copper in the periodic table. So that'd be iron, cobalt, manganese, nickel. They all fluoresce quite horribly and muck up your signal quite substantially. Of course, you know, the thing needs regular service. The resolution of the systems are, of course, limited by the geometry of it. Yeah. And therefore some structures that are very close together or have patterns that are close together are difficult to tell apart. Yeah. X-ray diffraction works in a very simple manner. It's wonderfully a wonderful probe for the structure of your materials, and it works a bit like you see on the in the diagram. Yeah, there's a two-dimensional representation of a crystal lattice. Yeah, and the diffraction effect is a very simple, basic combination between reflection and interference, and it causes one crystal structure to have a very clear diffraction pattern, which you can interpret as a fingerprint of the microstructure and crystal structure of your material. That is a beautiful part of diffraction, and it is extremely powerful in probing the structure of all matter, and that's probably why this method has been associated with the most Nobel Prizes in the history of this prize. And this could also be a reason why it is very interesting for you as well. Yeah, because each mineral, of course, has its own crystal structure. These lattice planes, which define the position of your peaks, are very characteristic for each different crystal and each different mineral. And the electron density, which defines each plane, depends on the elements in there, and they go into the intensity of your peaks. However, it is not those intensities of the peaks are not the most sensitive of the signal that you see. That's why it does not reliably give you the chemistry of your minerals, right? Okay, so what do you need if you've got a complex mineralogy that you need to be resolved? There might be some clays that need to be identified and quantified. If you have minerals under 1 weight%, that will get difficult. If you have a huge number of samples, that'll be challenging for a laboratory device. And if you want your results with a shorter turnaround time than months, then laboratory devices will probably not deliver this for you. And if you're on an exploration budget and don't have the cash to buy and sustain a laboratory for X-ray diffraction on your own, then of course laboratory devices will not deliver what you need. But luckily, there is something that can deliver all of those promises, and that is synchrotron X-ray diffraction. Now, synchrotrons work in a completely different way to generate X-rays. They rely on particle accelerators, which are huge research infrastructures to generate extremely brilliant X-rays and at extremely high energy. And this is exactly what we've used in our experiment. We use a high energy 75 kiloelectron volt X-rays. That means we can shine right through a substantially thick sample. So our sample is about 1.2, 1.3 millimeters thick. And then we can detect the whole scattered cone on a flat detector, a two-dimensional detector. And that means we can go down to below 0.1% as in detection limits. We have a 200-fold signal-to-noise improvement. We have a very sharp reflections, those peaks that you see in the diffraction pattern, and we can probe a large amount of your sample because we have this great penetration depth. And because of this extreme brilliance, we can measure within seconds. That means you have a capacity of tens of thousands of samples with a system like this. Obviously, we're still not great on the elemental composition. That's why assays still remain essential for a sensible analysis. Now you can see the difference here quite graphically between a laboratory and this, I must admit, is one of the best diffraction patterns that I've collected on my laboratory devices. So if you get a lab pattern that looks like this, you should be really happy about it. But the comparison to the setup that we've built at the synchrotron is below, and you can see it's just chalk and cheese. It is quite considerably sharper. It obviously has a loads less noise in the signal, and the background is very well defined. So you can see a lot of information in the diffraction pattern that you can collect at the synchrotron powder diffraction setup. So that means you can trust the mineral identification, because the reflections are sharp. You can see very closely related minerals and differentiate between them. And the added advantage is that you can get a huge number of these data sets in a very short time. This is an example of what you can get out of the analysis. Yeah, it gives you a list of course, all your gang minerals, but also all the interesting minerals for your recovery. It gives you a good insight into the trace minerals. You can see in this case, molybdenite is being quantified down to 0.02%. You get an astoundingly good handle also on amorphous content as well. Yeah? So if you have disordered or amorphous materials in your sample, then these can be quantified extremely well as well. Plus layered minerals, as well as all of the clay minerals, yeah, which can affect your flotation, can be quantified with in great detail as well. Yeah. You can get this. You obviously get this as a PDF report, but you can also get the comma separated values for your database or block models or whatever you need them for. This is a comparison of why we are able to deliver this. Yeah, the X-ray flux in the first line just shows you that we are 6 orders of magnitude. That's 1 million times more bright than the laboratory X-ray tube when we go to the synchrotron. Yeah, I mean, an X-ray tube is quite brilliant. It gives you 100 million photons every second, which is substantial. But a synchrotron is just brighter than the sun. It is incomparable when it comes to photon flux, and that is the whole reason why we can design an experiment that is this good. And that's why we only need seconds for an exposure for each of your samples. And that is why we have this huge capacity available for you. Of over 5,000 measurements every day. The 75 kilo electron volts I've already mentioned, are an added bonus because it does away with fluorescence of everything that matters. The resolution I've touched upon as being extremely good and helpful in understanding closely related minerals, and the probe volume is a really nice tool to just do away with all of the effects that are otherwise difficult when in the standard Bragg-Brentano setup, for example, preferred orientation, or these other surface effects that you might come upon. Now I'm going to pass over to our beloved, or my beloved CEO, Sebastian, who's going to tell you how this actually works in practice for the customers. Sebastian.
Yeah. Thank you, Bernd. Thank you, Callum. Yes. So if you are interested in working with us to actually get your samples measured at the synchrotron, it's pretty easy, and we try to make it as easy as possible. You ship us 10 grams per sample of the pulps, rejects that you already have. We prepare the sample, we measure it, we analyze it, so that you actually get a list like the list Bernd shared just a moment ago, and you get it into your system the way you need it to make decisions. So there's actually no site work. There's nothing you need to do specifically for us to measure to get the data. We can work with pretty wide range of batches. So you can send us 10 samples if you really motivated. You can even send us 1 or 2 samples, but yeah, like usually our customers start at 10 samples, and we can handle batches of 10,000. We can even handle more if you give us a little bit of warning. You see our turnaround time. So we measure every 2 weeks, pre-scheduled, and you can I can send you the schedule if you like. But that means if you send us 1,500 samples or less, you can expect the data within weeks, 1 month. For bigger batches, it will take us a little bit of actually it's a sample preparation. The measurement we can usually do in one beam time or two. So that kind of limits the turnaround time. But if you think 10,000 samples in 2 months, that's a good turnaround time for any measurement a method you can think of. So with that, here we go. To actually get to something like a couple hundred to thousand or even 10,000 campaign, this is our pipeline, not pipeline, kind of like how we get there is first, kind of like you need to talk to us, right? We want to learn about your deposit. What have you done? So what are the open questions? Can we actually help you? Is our method the right method for you? If we both determine that it is, we would go into a pilot. I will tell you in a second what a pilot actually all contains. That is where we actually go through a bunch of variations of our methods to find the ideal one for your ore, and then we have all the parameters for the campaign, and you can be absolutely 100% sure that you get the answers that you're looking for. So it's actually a very low risk investment to then go to a bigger number of samples in a campaign, and that actually advances your project and you can make decisions. And you see all the nice KPIs that Bernd said before. So in the pilot, you send us 10 samples, ideally a little bit more than 10 grams because we want to do a lot of different things with it. We take from every sample 5 times 3 subsamples. So actually 4 times 3 subsamples. So those are prepared as received, so not milled at all. 5 minutes milled, so it's actually finer than what is kind of like in the as received, and then 20 minutes, so it's really fine. But there is a risk that you could over mill. So that's the reason why we do as received 5 minutes and 20 minutes. With the 20 minutes, we also do a pair distribution measurement that is going into the amorphous content a little bit more, so to see if we can get informations out of that. Bernd can tell you more about it if you're interested in it. If you have lots of amorphous content, that could be interesting. And then an XRD for that is actually with a reference standard spiked and 20 minutes milled, so we can actually determine the absolute amount of amorphous. So with this, we do all the analysis, and that gives you then a full report on those 10 samples, and that report has everything in it that we learned from it. So that is already data that is valuable for you, but based on it, you and us, we can make a decision which of the processes, which measurements are the best for your samples. And if you send us from different ore zones, we can even determine for different ore zones, different processes. And with that, we can then go into, here we go, the big campaign. And the nice thing that we have for you as a participant of this webinar, if you book a call with me today, and there is going to be the link for this on the last slide, you book a pilot, and if you then decide to go with a campaign, we are going to deduct the cost of the pilot from the campaign up to 10% of the campaign costs. So if you decide on a big campaign with something like 1,000 samples, the cost of the pilot is going to be absolutely 100% deducted from that campaign. If you do a very small one, or like 100 samples campaign, then it's going to be up to 10% of the campaign cost. But I can explain this in much more detail when you come to that point. Your full campaign on Rails, that is then, we have the optimized sample preparation. We know exactly what we can expect from the synchrotron data. We have already a mineralogical model on your ore body, so that then runs through, and you get, as Bernd said, the data as a PDF report and as a CSV, so you can actually upload it into your model. And now here is the link. So meeting eu.hubspot.com/swinkler. You can also scan the QR code. You can also send me an email if you like to talk to us about pilot, or at least you're already, that would be fantastic if you can book a call now. But if you have any questions, now is the time to ask. But I have a question for Bernd at this moment. Is there a limit of theoretical, the theoretical limit of how many minerals we can actually identify in the most complex ore that you would send to us? I don't, at some point it's getting very crowded, right?
It can get very crowded, and obviously the intensities, as even in our data, go down when you have very small contributions, and then it gets more challenging. So if you only see one or two peaks of a trace mineral, then the reliable identification, let's put it that way, does become very iffy, very difficult. So I mean, I've seen quantifications with over 20 different minerals in there. There are even publications with more minerals. So, but I think getting over 25 is rather challenging. Yeah, but that is already a huge amount for a small sample. Yeah.
Mm-hmm. What about with clays? Is there like where I know we talk about that we can't do detailed clay specification, but what do you think? What is the limit there?
So it depends very strongly on the type of clay minerals that are in the sample. There are some clays which overlap quite strongly, and if you don't do any swelling experiments, then it can be impossible to differentiate between them, and that's that limitation we have as well. The advantage is that we can see the lattice parameters very exactly, quite reliably, and that, of course, we also have the advantage that we don't have this preferred orientation which you do have with standard laboratory devices when you measure clays. Then the clays, seeing that they are platelets all the time, no matter how fine you grind them, they will sort of flatten out in the laboratory X-ray diffraction, and this does not happen in our experiment. So we do have a bit of an advantage with that respect to clays as well, as over the laboratory devices. The number of different clays that I think we've quantified in a sample, that is sort of in the order of a handful, like 4 or 5 different clay minerals in a sample. That's what we can reliably sort of see. Yeah.
Very interesting. Now I have one more question. The milling, right? We do have different regimes in the pilot. Is that actually a real danger to over mill or under mill?
Yes, and that is quite mineralogy dependent, right? So the rocks that you can get out are very diverse, and the mineralogy is diverse, and that's why the physical properties of the minerals are also diverse. Yeah, so you can have very hard minerals like quartz, feldspars, or even corundum in your sample, and then next to it there will be something really soft, like a clay mineral, and those soft minerals are actually the ones that you damage the first when you do excessive milling. You change the mineralogy of them. You push out the water, you compress the layers, and that can change your clay identification and quantification completely. Yeah, and this is something that you really don't want to do when you're looking at mineral samples. And that's why we want to be extremely careful about how we identify these clay minerals. And that's the main reason that we always also measure the samples as they have been delivered as a first off, just to make sure that we're not breaking down the soft minerals during our processing. But the processing is also important to reduce the grain size of especially the harder minerals, so that they have a good statistical distribution over the measured range, and that we can get the most reliable quantification for these hard minerals in combination with the soft minerals.
Okay. Okay. So here, Michael is asking. Give me 1 second. I'm just going to mark this as a question, and then yeah. Thank you for the thorough explanation on how synchrotron measurements help to identify trace amounts of mineral phases. XRPD is indeed very strong technique to evaluate multi-phase mixtures. Having worked previously on mechanosynthesized tetrasulfides, I saw the importance on XRD. So that's not a question. Thank you, Mike.
But that's quite right, Michael. Yeah. The mechanosynthesized materials are a wonderful example of how XRPD can help even in the operando phase of these of the synthesization, yeah, or mechanosynthesis. Sorry, you can actually shine hard X-rays or high energy X-rays through a mill and identify what is happening while you're milling. It is phenomenal. Yeah. So. Yeah, this is one of the reasons I love X-ray powder diffraction so much, is it's so versatile. But that's nothing we do, yeah. So we don't offer high throughput mechanosynthesis or mechanochemical processing. Yeah, we just do ambient conditions, ambient temperature, ambient pressure, powder diffraction, but that of an amazing quality. Yeah.
I have a question to share you, Bernd, and that is, can we tell which mineral is hosting the element we're looking for? So, say we're doing copper, can we tell exactly where the copper is hosted, or gold?
Yeah, that's an excellent question. That's sort of one of those strengths of these more visual analysis tools like TEMO ChemScan, where you actually raster over a polished rock, and you can see how the elements are distributed. And if we detect, for example, gold or platinum, then we have no way of saying how it is contained within the rock. So we can't give you any sort of 2-dimensional or 3-dimensional ideas of the positioning of this element within the rock. So that is really something that you will have to rely on ChemScan or TEMO for. Yeah. There are tomographical techniques that might be able to give you information like that as well. However, as far as I know, they haven't been used in the petrological field that much yet. Yeah? But that's something that might be there for the future. Yeah.
All right. I think this is there any other questions from our audience? If not, I would like to thank you, Callum and Bernd, for this great webinar. Hopefully we can do more of them in the near future. I thank everybody who attended and is watching this maybe as a recording. You can still book a call with us to get to know us better and to explain to us what are the questions. Here, there's Pardeep is asking a question. What's the difference between normal XRPD and synchrotron XRD? Maybe Ben, you can summarize.
Yes, I'll do my best, Pradeep. So in principle, the technique is exactly the same. You shine X-rays on a sample, yeah, and that's sort of the fundamentals of it. And you collect the scattered signal from this from a multicrystalline or polycrystalline material, and if you do it in a laboratory, yeah, so with a normal XRPD, and that's what I'm assuming you mean with normal XRPD, is that you've got a laboratory instrument. They're typically sort of fridge sized. You prepare your sample in a flat sample plate and put it into your diffractometer, and measure it using typically a copper K alpha X-ray tube. Copper K alpha means you're using copper as an anode material, and you're using the characteristic X-ray lines of the copper anode to do the diffraction experiment. Yeah, because you need monochromatic X-rays. Now that's sort of the fundamentals of how you do a laboratory X-ray diffraction pattern. You have to measure typically sort of between 10 minutes for a really fast measurement, or 10 hours for a really high quality, low noise experiment, and you collect and you get the data, which you can analyze in the same fashion that you do analyze the synchrotron X-ray powder diffraction pattern with. So the synchrotron is just a different X-ray source, and it is really powerful in the sense that you have a wide range of energies that you can access using synchrotron source, and you have a lot more photons. So the synchrotron source is intensely bright, yeah, and because it is so bright, you can monochromatize your X-rays a lot more aggressively and get a lot sharper reflections than with a powder X-ray diffraction pattern. Because if you use the same techniques on a laboratory device, then you will end up not having any photons coming out of your optics. Yeah, so you can put in a lot of high quality optics into a synchrotron system and still get an immense X-ray intensity out onto your sample. And because of this, you can measure your data in a fraction of the time that you can do it in a laboratory system. So I'm talking about seconds for a brilliant data quality compared to minutes or hours in a laboratory device. In addition, there are some more technical advantages which I was trying to get at with respect to, for example, things artifacts that come from the sample preparation. So if you flatten out a sample in the sample holder for a laboratory X-ray powder diffraction, then you have to apply a decent amount of pressure. That's on the surface of the sample. Therefore, your crystals orientate themselves, and you get effects called preferred orientation. This is something that doesn't occur with the setup that we have, because we've got rather thick sample where we shine our X-rays through, and we've got a large two-dimensional detector, which is also different to the laboratory device, where you typically have a rather small detector area. So we measure our system or our data quite differently to a laboratory device, and therefore have this immense intensity, the high quality, and the high capacity that we do have with synchrotron X-ray diffraction. I hope that sort of covered what you were trying to get at. Yeah.
I have one more question before we wrap up, because I forgot about it.
Okay.
What about samples or kind of like ores that contain potentially dangerous stuff like uranium?
Okay, like uranium. Yes. So we do. We have had this question before, and we got a little bit, flummoxed by it. But now we're prepared. So we can measure uranium ores, yeah, that have not been enriched. that come straight, sort of basically your the ore body material, right? This is no problem for us at the moment. So there is so we can get the samples shipped to Germany for our preparation here in our preparation lab in Hamburg, and we can measure them at the ESRF using our sealed sample holders, because the sealed sample holders take only about 10 to 15 milligrams of sample, and our sample preparation lab is suited for dust-free sample preparation, which is obviously very necessary if you're working with radioactive materials, right? What we cannot do is anything that has been that's gone through an enrichment process. So we can't measure anything, any uranium, sort of processed uranium ores. What we this is the only thing, sort of limitation that we do have. Standard unprocessed ores are fine. That relates also to other iffy ores like asbestos-containing ores. This is we need sort of the same level of rigor in the lab to work with those ores as we do with slightly radioactive ores.
Yeah, and it would be good if you guys know, if you want to send us something like that, tell us beforehand. That's
Absolutely.
that is the one thing we need. Do we have any more questions? Happy to stick around. We have all morning for your questions if you have more. Otherwise, that doesn't seem to be the case. Again, thank you, Callum. Thank you, Barend. Thanks everybody for coming along, and hopefully talk to you soon.
Yeah. See you. Bye bye.
Guys. Bye.